Welcome everyone. Thanks for joining me for a deep dive on AWS App Mesh with Amazon EKS. My name is Jesse Butler, and I'm a senior developer advocate within the AWS Container Services team. So I'm really excited to be here and to talk about this topic. App Mesh can appear complex when first getting started. So in this talk, I hope to provide some context to help explain how App Mesh works, why we built it, and continue to add features, and ultimately to help you see how you can make use of it to solve real-world problems. I'll start today with a quick overview of what AWS App Mesh is, how it works, and what sorts of problems you might want to solve with it. I'll cover the high-level architectural components of App Mesh, and also the resources that you'll need to work with when using the service. This talk is called a deep dive, but I won't be digging in too deep. We'll definitely get into details, or hopefully just the right level of depth to be useful for you as you're looking to get started with the service. Once we sorted out how App Mesh works and how to use it with Kubernetes, we'll get into some demos. This is a pretty big topic and we can't hope to cover all of it, so I've prepared some demos that address some common use cases at a high level, which can be iterated on and used in a number of scenarios. For the demos, I'm going to be using an app that's available on GitHub, so you can pick it up where I leave off. Note, throughout the talk, I'll be assuming some amount of container and Kubernetes knowledge. However, I aim to keep the concepts understandable and generally applicable for whatever your orchestration environment is. So let's get started with an overview. I think it's important to set some context around the motivation for building a solution like App Mesh. Over the last decade, several patterns have emerged in how software is built and deployed. Containers are a great way to package, deploy, and manage applications, especially those built using a microservices architecture. There are many benefits in using containers, from packaging and dependency management, maintaining consistency through various stages of development, testing coherence, and ease of scale. That scale, though, can become difficult to manage, and it introduces new problems. These are sometimes referred to as day two problems. Getting a few services up and running in containers is a start, but when that grows to hundreds of microservices deployed in hundreds or thousands of containers, these issues arise. What exactly is happening in your clusters, and how are your services interacting with each other and performing against baseline expectations? How do you manage and monitor traffic between thousands of abstract compute environments? Are there standardized ways of automating policy and creating secure by default environments for multiple development teams? And ultimately, what can be done within the infrastructure to improve the overall experience for your customers? I think of these abstract requirements as cloud-native table stakes. You need the ability to reason about your large-scale deployments as well as you can small ones. Managing traffic between services addresses many critical needs, from simplifying canary rollouts and blue-green deployments to rerouting traffic away from problematic services. Security is paramount for your applications, and automating any aspect of security and policy enforcement helps work toward a secure by default infrastructure for running your software in production. Complex systems are complex. There's no way around that, and there's no magic in the cloud. So you need features that simplify the ability to increase the resilience of your systems, therefore improving your user's experience. We can further categorize these requirements. Observability is a topic unto itself. The practice of building systems with metrics, traces, and logs is not unique to cloud-native applications, but can be difficult and expensive to manage at scale in cloud-native environments. Traffic management refers to intelligent application-aware routing capabilities which provide granular routing and traffic shifting to implement various deployment strategies. With the ephemeral nature of containers at scale, you need abstractions and programmable logic here. Around security and policy enforcement, solutions like end-to-end encryption and certificate management and policy creation and enforcement imbue sanity in your large-scale deployments. Finally, resilience refers to functionality that allows your application to recover from failure scenarios dynamically, with features such as retries, timeouts, and circuit breakers. Ideally, decoupled from the application source code. When you're working with distributed teams and multiple microservices, these strategies can be a mixed bag. So being able to actually apply these across your application is really very helpful. So these are all categories that need to be addressed, and I consider them cloud-native table stakes. The service mesh is like a Swiss Army knife for these types of problems. With AWS App Mesh, you can solve for these problems and more. App Mesh provides a control plane that you interact with to express intent for configuration around your application and its traffic, and a data plane which is deployed alongside your application software, monitoring, managing all of the traffic on the wire. By virtue of its design, App Mesh is in a position to provide features to address all of these needs that we've discussed so far. I said there's no magic in the cloud, so let's get into some details as to how App Mesh works in order to explain how it can meet these needs. AWS App Mesh is a fully managed service mesh, which makes it easy to monitor and control the communications between your services. App Mesh standardizes how your application services communicate, giving you end-to-end visibility and helping to ensure high availability for your applications. It provides consistent visibility and network traffic controls for every service that you add to it. App Mesh supports applications running in containers in Amazon ECS or Amazon EKS, either using EC2 or Fargate compute resources. It also supports self-managed Kubernetes on EC2, as well as applications deployed on instances in EC2. For our discussion today, I'll focus on the concepts as they relate to containers, and specifically in Amazon EKS. As you can see from this wall of text, App Mesh has a lot of features. Some of these are exposed from the proxy software used in the data plane, which is Envoy. Envoy is an open source project, one of the first graduated projects in the CNCF ecosystem. Envoy is ideal for its role in App Mesh, given it's very efficient and highly performant. Along with Envoy's features, App Mesh offers additional features, functionality, and integrations with other AWS services. We'll refer to some new features on our roadmap toward the end of this talk as well. Our most recent release is the AWS App Mesh controller for Kubernetes, which I'll be working with today. We also have timeout policy configuration and Ingress gateway support in preview today, so watch for those releases soon. Let's get into the details a bit more on how some of these features are enabled. We can see here at the core of the solution, each deployed service has an Envoy proxy instance running alongside it. This implements the data plane. These Envoy instances receive their configuration from the App Mesh control plane based upon the configuration you provided, and the proxies manage the traffic within the App Mesh based upon that configuration. You can see integrations with various external solutions, including other AWS services, partner solutions, and solutions you may choose to manage yourself. Zooming in on a couple of services, you see the relationship between them and the Envoy proxy instances. The proxies are managed and monitored by App Mesh, and in turn they route traffic as needed. In this manner, all traffic bound for your application services flows through App Mesh's data plane and can be managed and observed. In this case, we see that the proxy for services A and B are intercepting traffic and routing to them. The proxies could be configured to send to a different version of the same service, a different service altogether, or to simply drop traffic. Staying zoomed in, but getting to Kubernetes specifically, App Mesh proxy instances are deployed as sidecar containers with an Envoy container instance running within each pod in the mesh. If the proper configuration is in place, which is quite simple to implement, these sidecar proxies are automatically injected by the App Mesh controller for Kubernetes, which also handles the creation of App Mesh components within AWS. I just mentioned the traffic for a given container is actually routed to its Envoy proxy container, which intercepts the traffic and then routes it based on the configuration you've provided. This is accomplished in Kubernetes by an init container, which among other things configures IP tables to route traffic to the Envoy proxy instance rather than the deployed app containers. From there, Envoy configuration takes over. If you imagine this construct at scale, where you provide the intent to configuration for any number of services to App Mesh configures the proxies as needed, and Kubernetes keeps it all humming along, you're basically understanding the business end of how App Mesh works. Next, I'd like to go over the various aspects of App Mesh configuration. This is where some of the complexity starts to creep in, but it's also your door into using the service. So I'd like to go over each component and the relationships between them before we try to use them in action. App Mesh leverages several abstractions that allow you to express the configuration for your service mesh and applications within. Whether you're using Kubernetes, another AWS service, or the CLI or APIs to manage this, these constructs are the global API of App Mesh, which you use to express your configuration intent to the service. The overarching abstraction here is the mesh itself. This is the logical boundary for network traffic between services that reside within the mesh. The service mesh contains all of the other constructs that make up the mesh. Virtual nodes are the construct used as a reference to components of your application. In Kubernetes, virtual nodes specify affiliation with pods and indirectly deployments, as well as services. App Mesh virtual services represent those services provided by virtual nodes and connect your traffic to them with other constructs such as virtual routers. The relationship between virtual services and virtual nodes and the related configuration is important to the behavior of your application within the mesh. Virtual routers can handle routing traffic for virtual services, and direct that traffic based on your configuration specifications. Here we see the virtual service named Paths is sending traffic to a virtual router of the same name. Virtual routers will then direct traffic towards your virtual nodes by specifying routes. Routes apply to HTTP, HTTP2, gRPC, or any TCP-based traffic. They're specified using match criteria, which can be path-based, based on header content, or service or method name. Configuration of these routes is what enables all the traffic shifting features of App Mesh. You can specify a relative priority for a route, and you can configure multiple virtual node destinations for a given route and weight the traffic between them. For example, to achieve a quick A/B test between two versions of a service, you can easily send 50% of traffic to one version and 50% to another. This can be used to simplify many types of deployments, canaries, blue-green deployments. We'll get into a demonstration of that toward the end of the talk. Some resilience features are configured through routes as well. For example, you can specify a retry policy for a given route and decouple that pattern from your application source code. I'll also show a demonstration of that later on. This configuration can then be managed through the route across a set of services and changed very easily at scale. Virtual gateways are a new feature currently in App Mesh Preview. This construct allows you to specify ingress rules for traffic coming into your mesh. While typically we're concerned with east-west traffic within the mesh or traffic between services, virtual gateways provide you the ability to define the path of inbound north-south traffic. So they enable resources outside your mesh to communicate with resources inside your mesh. Virtual gateways also use routes to define ingress rules and specify the flow of traffic from outside the mesh to internal mesh components. These are specified in gateway routes, which we'll show an example of. So here we see a slightly more explicit architecture diagram of a simple Kubernetes application running within App Mesh. Hopefully this makes clear the various components of configuration and their relationships. We see traffic ingresses through the virtual gateway, and its rules pass the logic flow to the Paths virtual service. It in turn forwards traffic logically onto a virtual router, also called Paths. From here, routes send traffic to one of two virtual nodes, foo service or bar service, based on the HTTP route prefix matching either /foo or /bar, respectively. Finally, traffic will end up at one of two Kubernetes services, foo service or bar service. There are some additional configuration opportunities within App Mesh, but with what I've covered so far, hopefully you have a clear idea of the various constructs needed to get your application up and running in App Mesh and how they all work together. So now let's talk about some use cases. We only have so much time today, so this will really be a bit of a whirlwind tour. Hopefully it's enough to get you started and you can jump on the documentation and our tutorial examples on GitHub to keep exploring. I'll share a link to the tutorials at the end of the talk. I want to quickly describe the demo app I'm going to be using. This is a very simple app that returns a string with a color in it based on a color value set in the request header. It's a useful demo application for our purposes because the more colors we add, the more moving parts in our cluster that we have to add to a service mesh. With a simple app like this, we can do interesting things in App Mesh without the app itself getting in the way or becoming a distraction. It's not meant to be a reference application that you might run in production. It's expressly built to show off some of the features we're talking about. Another reason to use this app today is, as I mentioned, there's a library of App Mesh tutorials available on GitHub, and many of them use this app. So when we're done here today, you can keep context while exploring different features. So this app hangs together in a pretty simple way. It consists of two services, a front-end gateway and a back-end color teller service. The front end is behind a load balancer, and it passes requests on to one of many color teller instances based upon the color passed. And here we see the color app deployed in EKS with App Mesh. Right off the bat, you can see that we have added some complexity in the architecture. However, keep in mind we're not here to just connect services in a new way. With this architecture, we have the same app running, but we're able to drop the front-end service entirely, and we can now use App Mesh to manage and monitor every bit of traffic within the mesh. That's pretty powerful for adding a few components. And the great thing here is that in Kubernetes, when using the App Mesh controller, all of this is managed for you. You simply define the components in YAML and pass them to the Kubernetes API, as you do with deployment services and other native Kubernetes objects. Given we've just released the App Mesh controller for Kubernetes and App Mesh Ingress is available in preview, installing the controller and setting up Ingress to our app is a great place to start. I'll first show you the Kubernetes objects required to configure the color app in App Mesh, then we'll head over to a terminal and we'll actually deploy it. First, we define a mesh. It uses a namespace selector to designate the mesh membership for resources in a specified Kubernetes namespace. Note, I've also added some labels to the application's namespace to specify both the mesh and its gateway. There's also the sidecar injector label, and when that is enabled, the controller will automatically inject the Envoy proxy sidecar into new pods and add them to the mesh whenever a new pod is created. Next is the specification for the Ingress gateway. You can see it also specifies a namespace selector, as well as network and health check configuration. As part of the overall gateway construct, gateway routes are defined. These specify the flow of ingress traffic. In this case, HTTP traffic matching the /headers prefix is forwarded to the virtual service color headers. This replaces the now deprecated front-end service in our application. Within this demo, a path-based gateway route is also defined. Here, HTTP traffic matching the prefix /paths is routed to a second virtual service named color paths. Now with a handful of lines of YAML, we've sunsetted an entire front end and added functionality as well. Moving on to the virtual services, we continue the logical flow of traffic and specify virtual routers as providers. In this case, you can see the color paths virtual service forwards traffic to a virtual router of the same name. There is a similar virtual router for the color headers virtual service. Virtual router configuration is where traffic branches off to one or more virtual nodes specified by the route configurations. As described earlier, routes can be based on path, headers, service, or method names, and they can be applied to HTTP, HTTP2, gRPC, or any TCP-based traffic. So here you see a route that directs HTTP traffic matching the /blue path to the virtual node named blue. Finally, we arrive at a virtual node specification. Here, listeners are specified for inbound traffic, and optionally backends can be defined as well. In Kubernetes, the service discovery entry maps to the Kubernetes service, and the pod selector maps to Kubernetes pods and indirectly Kubernetes deployments. Note the pod selector here is a simple mechanism which uses labels to identify which pods should be affiliated with this virtual node. This makes it quite simple to specify different nodes based upon version tags that we all commonly use. Using labels, you specify which pods belong to which virtual nodes. Here you can see that the blue deployment uses labels for the color app and the version blue. Similarly, the green deployment sets green for the version. Each time a pod is created, the controller will check these labels for matches and inject the required configuration. And here we are. So obviously this can be much more complex and contain multiple levels of services and routers, as well as external resources defined with egress rules and other configuration options. But this is a good overview to get started with the concepts. Let's pop over to a terminal and build all this out in a cluster. Okay, so we're going to get started with a fresh cluster running in Amazon EKS. It's got 3 worker nodes, and I'm just going to dump the config here to show that we're using the App Mesh and X-Ray add-on policies. And to get started with the App Mesh controller install, we'll create the App Mesh system namespace. And we'll use EKS Cuddle to set up an OpenID Connect provider and a service account with IAM role to provide our cluster access to the services we're using. I'm also adding a policy for App Mesh preview, so we'll have support for Ingress. Once that releases, you wouldn't have to do that. And with that done, we can now use the Helm chart to install the controller. I'm using a local copy here to enable App Mesh preview, but typically you would just use the published stable EKS chart for App Mesh controller. So now the install is complete, we can actually see the controller running and its version is a preview version. And we can also list out the CRDs that were installed. So we're actually ready at this point to install our meshed application. So we can see all of the objects roll out, the native Kubernetes objects, as well as the App Mesh custom resources. And each of those is actually reflected by the controller in App Mesh for you. So if we look in the namespace, we see we actually have a lot going on. This is effectively the Kubernetes objects that show the diagram that we were talking about earlier. And if we look at the pods, we actually see that there are several containers running in each. And this is the result of the automated sidecar proxy injection that we configured, as well as our choice to enable tracing at controller installation time, which we did. So if you actually take a look in one of our color pods, one of the service pods, we can see that our app is running. And we can actually dump out the rest of the containers as well, which are the X-Ray daemon and the Envoy proxy. So let's stow away the address of the Ingress gateway. That's the load balancer. So while we wait for that to come up, we can actually look in App Mesh and see that the controller reflected all of our changes in the App Mesh service. So here we see our mesh. And if we then wanted to say list our virtual nodes, we'd get a list of those. And we can check out that our gateway actually created, and that'll have the gateway routes as well. Those are independent objects, and here's our virtual services. So it looks like everything's okay as far as App Mesh is concerned. So let's give things a test. So here we're replicating the original functionality of the app. And also we can test our new paths capability. So with the app up and running in the mesh and Ingress sorted, we'll move on to looking at some of the other App Mesh features we can enable. Now let's see how we can make App Mesh work for us in addressing some of the cloud native requirement use cases we discussed earlier. One of the immediate and challenging issues with microservice architectures, especially in the ephemeral world of containers, is observability. We no longer SSH over to a host and peek at top output. There's no single monolith that's well documented and shipped with a single release. Today, applications are built by distributed teams using dozens or even hundreds of microservices. It's an organic environment and can be fairly chaotic. Over time, it can even be difficult to have a full picture of what's deployed in production at any given time. In this environment, how do you determine the current state of your applications and the health of their constituent services? What type of experience can you infer users are having right now based upon the health and performance of your services? If things go sideways, and they will, how can you identify and triage issues quickly? There's really no push-button solution here, but there are some common practices that have been refined through the years which offer a solid plan of action. All of this hinges on data. When we refer to observability, we're really talking about three different types of data which all work in concert to provide the overall picture of health for your deployed applications, and they help you triage issues as they arise. Metrics describe the behavior of a system over time. You know how a system should behave, and outliers will send up alarms about, for example, an increase in response time which might impact your users. Traces can then be used to determine specifics about a given point in time through the application stack. For example, you can use a set of traces to determine in which service this latency spiked in. And logs come from infrastructure and components of the system, but also from your own code. These are the breadcrumbs that we leave our future selves to help triage bad behavior. So to continue the example, maybe you find logs that indicate a data source became unavailable for a period of time, causing the increased latencies. Observability is a general term and not specific to App Mesh or service meshes in general. However, there are a lot of moving parts in such a system, and App Mesh can absolutely help make working with those moving parts much simpler. Given all the mesh traffic flows through the App Mesh data plane, it's in an excellent position to help you deploy and manage solutions around observability. Through Envoy, it supports a wide range of solutions for metrics, tracing, and logging. From open source solutions such as Prometheus, Zipkin, and Fluentd, to commercial products from our partners to integrations with other AWS services, there's a lot of options. This is a vast area and we can't cover it all here. So just to give an example of how App Mesh can make these tasks easier, let's look at a specific quick example of using AWS X-Ray to get some traces. First, what does it take to use X-Ray for our Kubernetes deployments? It's pretty straightforward, just a few simple steps required to configure and run an X-Ray daemon container in a given pod. The problem arises when doing this at scale and maintaining potentially hundreds or thousands of these container instances. When using App Mesh on Kubernetes, the controller handles this for you. You only have to enable tracing when installing or upgrading the Helm chart, which we did earlier. X-Ray is the default tracing provider, but you can specify different ones. There's a list of options on the Helm chart documentation. Keep in mind this is just one example of how the nuts and bolts of an observability solution at scale can be greatly simplified using App Mesh. Let's take a look at this now. So as we enabled tracing in the Helm chart when we installed, we really don't have any other configuration to do. So we're just going to drive a little traffic and then head over to the console and go to the X-Ray service. And there's a few basic things I want to show here. The app is not all that interesting, but I wanted to show that the service map is really useful when you have a whole set of services that you're looking at. It'll effectively show you all of the traffic flow patterns. As you can see, you can drill down on any one of these and you can see sort of at a glance faults and errors. You can actually see here the ingress is the root of all of the traffic coming in. The clients to the left are App Mesh health checks. And so you can actually see various types of representations of each node. And if you bounce over into traces, then you can see all of your endpoints. And if you drill down, you can then see all of the various requests that are coming in, and you can sort them in different ways. So here's a recent one. And if we actually jump in there, you see the spans for both the App Mesh component as well as the service underneath. So if this were a several microservice deep call, you would be able to drill down at this level and see, okay, here is the span. We get this overview information. You can see what the method was, what the status was, and you can see the overall flow. So this is really useful when you have something that your metrics are pointing to and you want to see which service is actually responsible for a certain outlier behavior. And if you go into analytics, you can see a nice representation of sort of what's happening, where you see the various codes that are happening. We actually have one 404 that was probably a load balancer that failed when it was coming up. But you can see all of your paths and you can see the distribution across them. You can also see the different methods and sort of the distribution of your traffic and effectively all of the various characteristics of the traffic coming into your application. So this is a pretty basic application, but still a meaningful demonstration on App Mesh, making it super simple to launch and manage observability resources. Next, I'd like to talk about another cloud-native requirement, resilience. App Mesh provides a number of features which allow you to apply resilience policies across your application, typically in route configurations and sometimes directly in a VirtualNode's listener specification. These include retries and timeouts, which is currently available in preview. We're also working on some new features in this space, including circuit breakers. Applying retry and timeout logic in the mesh allows you to address common problems with global policies, removing handling these routine problems from your microservice code, where they may be handled differently from service to service or from team to team. Again, drilling down to one example, I'd like to show how straightforward it is to apply a simple retry policy to improve the resilience of a service which depends on a downstream service which is inconsistent. You do this in App Mesh by specifying a retry policy on a given route. This includes configuration for retry actions to take and what types of events to issue retries for. In this example, App Mesh will configure Envoy to retry on any server error up to 4 times, waiting 2 seconds between each try. Let's take a look at that in action now. So to show how App Mesh can help increase resilience with retry policies, we'll make some changes to our application and inject some faults. So let's get some traffic running, and this time we'll show the HTTP status code so we can keep an eye on the faults. And we'll roll out a new version of the backend services, which return to 503 for roughly half the requests. And this simulates a scenario where you have a set of services that are calling out against something finicky, maybe a downstream data service that's experiencing transient outages. And as those pods roll out, we should start to see some failures. Yep. So we could go into each service's code and actually add retry logic, but we can do this really easily and globally across our application with the simple route configuration we were just talking about. And so once that settles, it was very quick actually. Our errors are gone. So our retries are taking care of our traffic. And the configuration is super simple. It's just these few lines here. You add that to a route and you can specify what the retry policy is. So I'll just flip our pods back and the route configuration back to the original state so we can go on with another demo. Another obvious benefit of all the traffic flowing through the App Mesh data plane is the ease of managing the traffic itself. There are a variety of features that we've discussed already that can be applied to your intelligent routing configurations in App Mesh. And they are applied across a wide variety of traffic, HTTP, HTTP2, gRPC, and anything running over TCP, as we discussed before. I'd like to drill down on just a couple of specific aspects of configuration, which are super powerful. Both of these cases rely on a single configuration feature to accomplish the goal. First, we could talk about A/B testing. If you're not familiar with the strategy, the idea is to have two or sometimes more groups testing different versions of an application. There's usually a control group, but this isn't academic, so we'll just stick with the basics. We'd like to deploy two versions of a service, say alpha and beta, and shift our user traffic to the correct version based upon that user's group, whether they're the alpha testers or the beta testers. To accomplish this using App Mesh is as simple as injecting the user's group affiliation into their HTTP request headers in your app and setting up a header-based route to the correct service. It's pretty straightforward. App Mesh makes a number of deployment strategies like this simpler to implement and manage. Blue-green deployments are a common update strategy, not to be confused with the colors in the app. It's all blue here, unrelated to the deployment strategy. We can call that red-black to make it even more confusing. The idea here is that you deploy the new version and it's waiting in the wings with no traffic routed to it. At some point, you shift production traffic over to the new version, replacing the old. And you can do this incrementally and monitor the metrics and the overall health of the application as you do it. If things go well, the new version gets promoted to prod. If they don't go well, you can always roll back. This is typically combined with a rolling update strategy where the shift from blue to green or version 1 to version 2 is done gradually. What I'll show here can be applied to a wide variety of deployment types, blue, green, canary deployments, really any time you need to shift percentages of traffic between different versions of a service. App Mesh can make it easier. You configure these sorts of deployment strategies in App Mesh by using weighted targets. This is a component of your route specification, and it provides granular control over routes to multiple virtual nodes. In this case, you see that I've defined both Blue v1 and Blue v2 virtual nodes, which in turn both represent pods in my cluster running v1 and v2 versions of the service. I can now easily shift percentage of traffic between the two with ease. You can also just set 0 on a route and very easily disable traffic to a problematic service. By the way, Weave has a really cool project called Flagger that provides further abstraction and automation in this area. It allows you to specify the deployment strategy as well as the metrics thresholds for increasing rollout or decreasing and rolling back. It's all automated and makes things like rolling updates and canary deployments really simple. It's very cool. You can check that out at flagger.app. So back to our basic demo here, as shown, the configuration is fairly simple if we just want to shift traffic between two versions of a service. Let's do that now. So let's say we feel our customers would benefit from louder colors. So we can test that out. I'll start with a canary deployment and shift 5% of traffic to a new version of the blue service that gives us a louder version of itself. So we send that deployment off to Kubernetes as well as a definition for a virtual node and a virtual router update to send 5% of traffic to the new version. And we see they start to creep in there. So the idea here is that you monitor your metrics and the overall health of the app and you increase your percentages. So here we're actually now shifting 50% to the new version, and you see that increases as soon as the configuration settles. So say you want to promote this type of change to the application. So you can actually deploy new versions of all of the backend color services, and we'll call them, say, louder. And they'll all come along with their own virtual node specification as well. So now we have that deployed. And as soon as those pods are up, we can, so they're all ready. So now we can apply a routing change to, say, send 25% of traffic to the new version. And now we're talking about more of a blue-green deployment. And as we can see in the output, we start having some of that, the louder colors come through. So the idea is, of course, you monitor the metrics and you increase the percentages over time. So maybe eventually you're at 75% and everything looks fine. So effectively you shift 100% of your traffic to the new version and you deprecate the old. And at any point, of course, if you needed to, you could roll back. So once the configuration settles, it was pretty quick. We see that everything's loud. And that's a horrible idea. So let's just restore it and we'll remove this louder version of the app. We can actually, so we can delete those and change our configuration on the router back. And we're back to normal. You can see how all sorts of strategies become super simple to implement and roll out at scale using App Mesh. This is fairly easy to automate in Kubernetes as well, as it's all just done in YAML. Hopefully that gave you a good idea of how App Mesh works, how to work with it, and what sorts of problems you can solve with it. It really is a Swiss Army knife, in my opinion. It can help solve or automate solutions for a lot of cloud-native problems. If you're interested, as I said previously, there are more tutorial examples and demos on the AWS App Mesh Examples GitHub project, which I've linked here. Also, you can review both the AWS Containers roadmap as well as the AWS App Mesh roadmap on GitHub. Here you can see what we're currently working on, add your support for the features you'd like to see, and suggest new ones as well. We're currently working on a number of new features for App Mesh, including MTLS, circuit breaker configuration, and outlier detection, which will all help you to add resilience and security aspects to your applications. And with that, thanks so much for joining me today, and please reach out anytime with any questions or comments. We can now open it up for questions. Thanks again.